Hey everybody. Please feel free to ask questions along the way. And if you feel like you might like to come on this show one day yourself, please do get in contact. My contact details on the channel's About page. Next week, we'll be talking to Guy DuPont, but today it's Greg Davill. Hello, Greg.
Hello, Addy. How are you going?
How are you doing?
Good, thanks.
Good. Would you like to introduce yourself? Just tell anyone who might not know who you are, a bit about yourself.
Yeah, my name's Greg Davill. I'm electronics engineer, maybe a bit of a maker as well, and probably known for posting macro photos of electronics
Yep.
on Twitter, and showing the step of designing, soldering, photographing electronics. It's kind of what I do. I kind of like to work on small hobby projects and
Nice.
using electronics to solve problems.
Yeah, I have to say I'm very appreciative of how open you are with your rework and various other things. It's always good to see issues that come along, rather than just like perfect final piece.
Yeah, I end up with a lot of rework. Most of my designs, I like to get a design to a point where I think it's 95%, 90% going to work, and then hit the buy button. And instead of spending another couple of weeks, going through with a fine-tooth comb. So
fair enough. Yeah, and the practice
often that ends up with with a pin or two in the wrong spot, or you get to programming it and a peripheral can't be routed to a pin or something. But it's nothing that the the old microscope there in the background can't fix. With a bit of patience and soldering. And luckily, my hands aren't too shaky if I get my caffeine levels just right.
Not no caffeine, then it's just a little bit of caffeine, right? The right amount.
Yeah, or if you've already had coffee for the day, you've got to keep taking it in.
I see.
If you get a little bit too shaky, right?
Nice. Cool. So if we start then with your background, you willing to talk a bit about school and how you maybe got interested in this field and got started with it?
Yeah, sure. So I guess growing up, I was always tinkering with electronics and taking old consumer electronics apart. So I always went to the school fair and picked up, it was called Trash or Treasure.
Nice. Okay.
Basically, people sold all their junk to the school, and then people would buy it back from the school, and then the school kind of makes a profit, and everybody ends up with different junk in their garage. So I came home from that with a lot of old school computers, old scanners, printers, VCRs. Take them apart and just see how they work inside.
Fantastic. And that was kind of got you hooked at that stage.
Yeah, a little bit, and then trying to work out how it all worked and how people actually designed this, and basically teaching sand to think. I guess it's kind of where we've come now with microcontrollers, but a lot of these products predated any kind of computer, really. So, or very little computing. In a VCR, the computer probably just runs the on-screen display and stuff.
Yeah. I was going to say that the mechatronics and stuff behind a lot of this older stuff is fantastic. The way that they've got micro switches and whatever, just running the show.
Yeah, exactly. So after that, I kind of found a bit of interest in it's called the Pickaxe system. Okay. It's basically a PIC microcontroller. In fact, I think it's a UK-based company that developed that. Basically a PIC microcontroller that ran an interpreter on board, and you would program the EEPROM of the PIC in compiled BASIC. I think it ended up being
interesting
over a serial link, and so you could peek and poke registers, and they had their own kind of subset of BASIC that you would write. And that kind of got me started on embedded programming.
Okay.
I don't think I've touched BASIC in 10 plus years at this point, but that's where I got started. It's a pretty good step to skip needing to understand anything about the machine code, compilers, the programming aspect. I guess nowadays I'd say it's equivalent to a Circuit Python board or a MicroPython board, where
nice.
you can basically You know, Python is the language, but you basically can just plug in a serial terminal or, you know, via USB, and you can start coding away.
Amazing. Very
Yeah,
cool.
no, like it really lowers the barrier to entry for that kind of stuff, right?
Yeah.
So gets people hooked.
Brilliant.
And then from there, yeah, just went through normal school, uni, electronics
what did you do at uni
engineering. Yeah, electronics engineering.
Okay.
Doubled with computer science.
Right.
That's the traditional route. You know, in high school, I knew I wanted to do electronics, kind of coming out of high school. So didn't have a job lined up straight out of high school. So
Yeah.
get the degree under my belt. But I think in the position I'm in now, I don't necessarily have needed the degree, but it's kind of proved to myself that, you know, I can do this stuff, and some of the background understanding is handy to have as well.
Yeah, yeah. It's an interesting topic, the formal education side, because we've spoken about it before with Timon, and yeah, it's very interesting, isn't it? You know, the way that actually I'm not necessarily convinced it's required anymore, but people will still ask for it on job specs and various other things.
Yeah. I mean, I think even if the job I've got now doesn't explicitly require it, I think it's good to have, right? You know, especially further down the line. I mean, I guess once you've got a bit of a career history, it might not be as important, but it's often, even if it's
kickstart you
not important, it's still a checkbox that could, you know, disqualify you from some positions.
Fair enough.
But it's interesting. I was, you know, designing and building and, you know, even sending off Gerbers to Chinese manufacturers in high school.
Oh, amazing.
Well, Chinese manufacturers. I was using batch PCB a lot, which I don't know if you remember those, but that was a SparkFun offshoot where they basically did PCB pooling for you.
Yeah.
And I think, I don't know how many Chinese fabs were offering direct pooling services at that point. I think probably not too many. And they kind of picked up on it as a bit of a
good route,
a market segment moving forward. But yeah, and then through university, over 5 years of university, I designed one circuit board for a course. Because it's a very small amount of the curriculum, really.
Right. Okay.
Circuit board. I guess when you're trying to teach electronics engineering,
there's a lot of theory and stuff.
You want all the basics, the theory, the maths, Fourier transforms, you know, inductors, capacitors, you know, electromagnetics, how everything ties together. And it's like, by the way, there's this, like, you know, you can connect copper traces on a circuit board. You know, that's one thing that electronics engineers do. You know, so it's interesting, you know, and I already had experience with that. We were using Altium Designer. I think they allocated about 3 hours in the lab, and the circuit board was, I don't think I've got it anymore, but it was a 3 filters, so like a high, mid, low audio filter. So you could adjust different, I guess it's like spectrum of audio traveling through. So it was really just some potentiometers, some op amps, and passives, and we had to calculate all the values and stuff. But the circuit board layout, I think, took me, I don't know, 20 minutes or something out of the, you know, from opening up a project to, you know, can you check my work? And then they didn't really know what to do. That some people were still fussing around with how Altium worked, because we're using Altium at uni. You know, it's a pretty beast of a software if you've never touched any kind of computer-aided design before. So, but no, it was interesting. Good stuff. Yeah, it kind of goes to show, you know, and I was designing circuit boards through uni, but not for uni, right?
Yeah, it's interesting, isn't it?
So,
well done for keeping it up in your own time. It's looking back on my course, that was a frustration that I didn't have more electronics. But anyway, I wasn't really doing an electronics degree, so there you go. So out of uni,
I think that's also important to get a bit more like diverse viewpoints into engineering, you know, and into electronics. So, you know, there's a lot of artists and, you know, physicists need to use electronics as well and stuff like that. So Yeah, I mean, I think it's good to have people from diverse backgrounds and stuff. So
yeah, nice. And so then out of uni, you fell or came into a job quite nicely, which I think is where you're still doing a lot of work. Can you tell us a bit about that?
Yeah. So through a school friend I knew, they put was no secret during through high school that I was into electronics. So my school friends like, oh, I need somebody that's good with Arduino for a position. So
Okay.
of course, and they knew Arduino meant something about electronics, and so put my hand up and took along some projects to show off at like a meeting with my new boss, and he was. I think he said later that when he saw me come in with projects I'd already built, he was like, "Oh, he's hired already." But I think allocated about an hour, but we spent like 3 hours talking about various electronics, work that I'd done, and up to that point as probably more a bit of a hobby, and then also the projects that they had been working on and then were looking to move forward to. So at that point, it was more of a software project with Spatial Scientific to do aerial mapping work. So
Okay.
mostly a
So by
software
software,
problem.
by software here, you're talking about embedded software on hardware that exists, or is this more sort of abstract PC based?
Desktop
Yeah.
class software. So
Okay.
basically just navigating a pilot about where to fly in order to capture images over the ground with enough overlap and over the project area that they're trying to capture and stuff. So you basically feed a GPS signal into a computer, and then it's just a computer problem to show where the pilot is.
You're heading,
and they just needed a way to, from the computer software, send a signal out to basically activate the remote shutter on like a DSLR camera.
Okay.
That would be pointing down a hole in the floor in the back of the aircraft. So that's kind of where I got my start. The previous engineer at this company had built a Arduino project, so that's where they wanted help, maintaining that, keeping that working. And then when I came on, I, developed custom circuit boards for them, and then kind of put a lot more effort into the embedded side of things. And that's kind of, been interesting. With a lot of interesting projects come up over the years. And
yeah.
Are
you able to tell us about a good project in particular that you've worked on there?
Well, probably the most interesting is the so we start with just wanting to activate a remote shutter signal on a DSLR in the back, and now we've moved forward. For a while we were developing systems with the Hasselblad aerial camera, the A6D, which is interesting. I mean, it's at its core, it's pretty similar to a DSLR. It's like an image sensor and a lens, but they, instead of having like a little plastic remote shutter or a headphone jack, that you plug in the side as a remote shutter, it's got like higher spec, I guess, like LEMO connectors, and the USB cable is locked down and stuff. And but it's still fundamentally the same signal, that we have to send to the camera. And then moving forward, I guess, to almost like a different realm is kind of touching on thermal cameras, where a lot of the time the camera, you don't have control over the actual shutter mechanism, or like, you can't tell the they call it a focal plane array, like the sensor itself, you can't actually tell it to capture a single frame. The way they operate is it's kind of like a rolling shutter. The electronics in it go through and clear out the pixel values and then kind of read the next ones in sequence. So you end up with streaming data, which is kind of what a lot of thermal applications want. They want like a video feed. But for us, we want to capture a single frame in time. So it's kind of how do you, from like an input signal for like, we want to capture a frame.
Yep.
How do you then
actually
go
produce
to
one?
output just a single frame and going, this is exactly the time this was captured. And, this is all the frame data. This is like a timestamp of the frame. And a lot of the cameras don't provide that out of the box in a easy to use way, like with the timestamping feature. So, moving from starting with like writing Arduino code, some of the projects with thermal cameras have moved into FPGA territory, where we're capturing this parallel data stream. We're also capturing some timing signals that are coming out of the camera, VSync and HSync signals and frame start signals and stuff. And that way we can bundle them all together in a single kind of data packet that we then forward off to the computer. And with some newer projects, we're now kind of like fusing IMU data with the thermal images.
Okay.
Kind of at the camera.
Is that kind of stabilization type processing, or is that something else going on there?
Yeah. So we're using. In fact, I mean, I could show you this one here.
If you're able, yeah, that'd be great.
We're using these SPG IMUs. So SPG is a French company, really. Right. And it's a MEMS IMU, but it's it's kind of MEMS accelerometers and gyroscopes and a GPS or GNSS receiver in there as well. And then SPG's developed their own, the quality of an IMU is kind of all dependent in the Kalman filter, or like the way it combines IMU, gyroscope, position, altimeter, like all these various inputs, and then to just give you like your pitch roll, or and position, kind of like to tell you exactly where you are. Because if you're just looking at all these IMU values, it's kind of, you don't actually really get information about where you are, where you're positioned. There's actually a lot more maths behind it. So these are IMUs basically we could basically just tell them to give us a position. In fact, in a lot of our systems, we're using just a version one step higher that gives you a dual GPS input, so two antennas, and then they're positioned on an aircraft in such a way that the IMU can determine its angle, like it's yaw, without needing to use a magnetometer.
Right.
Because relying on the Earth's magnetic field for that stuff in a very noisy, electromagnetic noisy environment has proven not to be very ideal.
I can imagine. Yeah.
So it's interesting, just with two antennas, basically the IMU always knows which direction it's pointing. And then we take that data and basically with the FPGA, we can sync up the IMU and camera perfectly. So often we can either take a pulse out of the camera or give the camera a pulse, a periodic pulse, to sync it up. And then per frame, they're kind of paired together, the two data sources. And then we basically just shovel all that data to a computer. And at the computer's point, it's looking at working out where the camera is in space,
where
the image is projected to the ground onto like a terrain model, to then perform real-time stitching of images together.
Magic. That sounds awesome.
So it's kind of like you're painting a thermal image on the ground. I mean, when you look at still frames, you might be in a corner, or you start banking, and you're just looking at this square frame if you're looking at a like just data out of the camera itself, and you can't really tell, when a plane banks, the square frame of the camera is actually turned into a bit more of a keystone shape on the ground, like it's like a sideways parallelogram. And like with IMU data, you can actually visualize that. You won't get a square on, projected onto something like Google Maps. You'll actually get the shape.
That's fantastic.
So that's interesting, and that's part of the work we've moved into for a company called Fireflight,
right?
Which is we're basically trying to work on real-time fire mapping systems.
Okay, so this is a matter of there's a bushfire or whatever, and someone goes up in a plane and says, "This is the shape, this is the boundary," and keeps everyone up to date. Is that kind of the plan behind that?
Yeah. So often the way things operate now is there'll be they deploy a helicopter with a fire spotter that kind of will fly around over the top of the fire boundary and kind of indicate on a map where the fire boundary is.
Yep.
And get a bit of a lay of the land, work out, kind of project where it's going to go, and then they can use that information to deploy firefighting assets, as needed. So our system, it's kind of envisioned that it would operate in a similar way, but it would probably be deployed to fly continually over an area while the firefighting's happening. We've been in a trial phase with the local fire service here in Adelaide for the last fire season, but we didn't really have very many fires this season, which is good, but it's
good but frustrating for you.
It's like this kind of all kicked off, I guess, with our, was it 2020, or I think it was the 2020 fires.
Right.
Were pretty bad here. Not too bad in Adelaide, but on the east coast of Australia, definitely though, it's probably the worst worst fire season we've had for a while.
So the plan is that
I guess now there's
help.
no. Yeah.
Great. Okay, so you mentioned earlier that you've been quite lucky with Fireflight and your current job, in that you can do a bit of extra stuff on the side. And you mentioned some Linux work and how that sort of challenged some mindsets and sort of a new thing for you to explore. Can you talk about that a bit?
Yeah. I guess it's
obviously not the work itself, but the
I'm not coming at it completely fresh, because I do use Linux. Linux on the desktop, as they call it. It is the year of Linux on the desktop, right? So I use that for most of my embedded stuff. Everything you can basically do in Linux. And I like the extra power that it gives you over the development environment and stuff. So that's good, because if you're coming at it completely fresh, it would be a lot more bewildering. But no, I've got some projects that basically exceed the capability of like a typical microcontroller. Some of these in particular, that have fairly high resolution camera inputs and like Wi-Fi, needs and stuff. And I guess once you're dealing with like networking and a user interface and a camera, or like you're kind of getting into the realm of wanting an embedded Linux system rather than just a microcontroller.
Yep.
Like this project wouldn't operate on something like an ESP module or anything. So kind of pretty early on worked out this is what we need. And now it's like, how do we get there? So trying to work through, I'm probably the same as a lot of other engineers. I've got a drawer full of embedded Linux dev boards and Raspberry Pis and stuff. pretty much every project I've used a Raspberry Pi on, I've just used somebody else's pre-baked image.
Yep.
Just load the image on, power it up, and then you get a web page to do the config and stuff.
Stuff happens. Yeah.
But there's actually, I guess, quite a lot of work goes on behind the scenes to get to that point, which now I'm having to dig through the weeds and work out how do you set up a Linux build environment to generate that image file. How do you get scripts into that image, and
so you're using Yocto or
cross compiling and
Are you using Yocto or Buildroot or something similar?
I'm using the setup provided by the SoC manufacturer. They've provided a
BSB
or quote unquote SDK, but it's really just like a build environment.
Right.
And some sample applications and sample code and stuff for their peripherals that are in the SoC. So this is an SoC from Allwinner, and there's Allwinner products you can buy, like Raspberry Pi clones with Allwinner chips on them.
Yep.
But unfortunately, I'm not that lucky. The chip that we're using isn't popular in kind of open source hardware stuff. So I'm talking to some of their applications engineers to get details directly. It's not really a very popular, like if you search the chip, when we started the project, searching the chip on Google, we've returned almost 0 results.
Yeah, you'd swear it doesn't exist.
It's a chip they build and it's in products, but it's not really, it's not one of their popular ones, which is unfortunate because it means it doesn't have upstream Linux support. Like there's lots of little caveats that I didn't really realize throughout the selection process. You see the data sheet and it's like, oh, this has all the specs I need.
Yep. Does it have the software component as well, the drivers and everything? Yeah.
Well, yeah, you hope that it does. It's like this one in particular, I think they just pull the data sheet headlines. It's like, oh, this will support DDR2, DDR3, DDR3L, DDR4.
Right.
And then you actually, once you get some more information about it, it's like, oh, actually, they've not verified DDR4 or DDR2. It's really, they've only picked one, but the controller that's in the SoC can do all of them.
Yeah, it's IP.
They've only actually validated one.
Yeah.
Interesting like that. It's like the divide between, the hardware could support it, but the work involved on the software side would mean it's cheaper just to buy a different chip.
Yeah.
If it's a feature you need.
And so was this?
And then getting the actual data sheet, even though it's semi-complete, there's sections like the DDR controller that's all it is. It's a headline, DDR controller, and that's the one page. And there's no more details about it, which is very different from microcontroller space, where I don't think I've ever seen a microcontroller that kind of contains almost like a binary blob of silicon, where they're like, it has this feature, but we're not going to tell you how anything. Well, maybe I've not looked deep enough. I think initially some of the ESPs had a little bit of stuff like that, but they're pretty much all documented now.
I think what happens with the larger SoCs is that they actually buy in the IP from someone else, and they'll just plonk someone else's design in for DRAM and whatever else it might be. And so they're then under certain restrictions on what they can share as well in terms of data sheets and documentation. It gets very painful from there. So
they've only got the evaluation license,
Oh no. Anyway, so that's really frustrating to hear. But did you do the hardware design for this, or is it a SOM or something that you popped down in?
Pardon?
Did you do the hardware design for the actual
yes.
stock and the DRAM or
so they, in fact, I was provided with a DRAM layout. In fact, I may have even showed that on Twitter. It was in a different, a interesting EDA format.
Right.
I can't remember what format, something like PCAT or something. I don't know. It's like a text-based description I mean, like KiCad is as well now. If you were to copy an area of KiCad, it's visually it's like a track goes from this point to this point, and it's all kind of in text format. It's not a binary format. So I took that text format. I could see that it was describing where traces were going, and it would say like net name, trace from here to here. I took that and wrote a quick Python wrapper to convert it into a KiCad layout.
Okay.
And then realized that the layout they'd shown puts the DRAM chip kind of off, kind of like at a 45-degree angle,
right?
From the SoC, and our board was very space constrained, and we didn't have enough width to do that. We basically had to place it directly below, not off to the side.
Okay.
So against the judgments of the data sheet saying only use this layout, basically if you make your own layout, they won't support you if you have problems with timing or anything. I mean, so like they provide a reference layout, and if you don't use it, you're on your own if you hit any problems.
Right.
Yeah. So I did all the routing myself. I mean, I don't think DDR routing's that tricky once you've, I've done a couple of times now on the Orange Crab and the Butter Stick for DDR3. You really just, in my mind, I'm just trying to keep the number of vias in each trace kind of consistent. That way, in theory, they kind of cancel out. You don't really have to care about what signal propagation, specifically like signal propagation delays, look like, because every trace has a via in it. Like that's my thinking. It's like, so on a lot of these, it's like there's 2 or 3. And I think, you could measure the board thickness, and then it's like, if you're going from, people get very stuck up on this. It's like, if you're going from layer 1 to like an inner layer, you're traveling a shorter distance through the via for the signal propagation.
And it's like, things as well, unless you start back drilling.
Yeah. Well, at the frequencies where at stubs, it wouldn't really matter. Yeah. So, in fact, I don't think any of especially on the FPGA side, on the layouts I've done on the ECP5, I calculated it once. They can only run the pins up to 800 megatransfers per second. So it's about half the speed that the RAM would run at anyway.
Right.
And often designs don't even run it that high, because basically the clock ends up coupled to the CPU at some point, and often you're not able to get the clock that fast at the DRAM anyway. But if you're running the pins at 400 megahertz or 800 mega transfers per second, because it's double data rate, rising and falling edge, I think I calculated it's, if you shrink your clock by 10%, like you allocate like a 10% buffer for kind of the clock jitter, or the propagation kind of jitter between signals, skew between signals, you can get by with like a 1 centimeter difference between tracks. And it's like, well, why are we trace matching these down to like 0.5 millimeter when it doesn't matter? Like specifically for signal skew, it doesn't matter.
Very interesting.
It's a fun problem. Like I wrote scripts in KiCad to show a group of signals and the length of every signal, and then like show if it's above or below like a tolerance that you set, or a length that you set. And that's been built on top of other people's scripts that have done similar things. And it's kind of a fun problem, changing the length of a signal and going, oh, now it matches all the others, or oh, this one's too long, we got to shift some signals around. And, I like that part of like the design process, but in the end, it's actually probably not really required to go to that level of detail. But
sure. I mean, I know that with Altium, for example, you've got the length matching. It can do it in stages. So if you have 4 DRAM chips, for example, and your processor, you can actually do the first leg, match that, and then do the second leg and match that, and then third leg, etc. So presumably there's some good reasoning behind this.
Especially once you get up to multiple chips, I think it becomes more of an issue as well. All of these are just single, like an SoC to a DRAM chip.
Right.
Like it's point to point pretty much. I mean, once you get into, definitely on the SODIMM sticks that you put into your computer, they've got 8 16 packages on them. In fact, JEDEC, JEDEC, they publish Gerbers, I think, for a couple of the SODIMMs.
Oh, I hadn't realized that.
In fact, possibly all of them. I think they're free to download, and so you can see it's like, oh, this is an 8-layer board. Right. This is how they route the 64-bit or 128-bit width signal, out to all the DRAM chips.
Interesting. Okay.
And it's interesting to look at. I picked up one of those when I was doing some of this routing, just to kind of see how they do it.
Yeah.
But it's a different problem at that point because you're trying to route your signal through 16 chips, so it does actually matter a lot more when signals arrive at each chip.
And the stack up and things can be considerable. If you're matching the entire length rather than segment length, then you get considerable skew at like midpoints and things like that. But
and you probably want to be a bit more careful about measuring the actual propagation length rather than the signal length. Because the signals propagate differently on inner layers to outer layers. But on a lot of my designs, I just basically put the DRAM chip as close as possible to the SoC to give me enough room for routing.
Okay.
And then that's it's an easy way to deal with that.
So was that your first SoC with DRAM type layout that you did for this project recently? And did it work? I guess is the big question.
Yes, like the first layout. Previous to that, as I mentioned, I've done some layouts with the ECP5 FPGA. So unfortunately, once you're working with an SoC,
it's a little bit more out of your hands, isn't it? The setup and
the pins, basically they're like, oh, these are the pins that you have to connect to the DRAM. You can't really change them around. On the data pins you can change, but you do need to make sure all the address pins are in the right spot because they don't let you remap those. Even if the underlying controller IP might let you do it, they don't give you information about the registers that would let you poke at that kind of stuff. So this is the first layout I've done connecting DRAM to an SoC. It was LPDDR3.
Okay.
So it's basically a fixed 32-bit width that you've got to 32-bit. Width that you've got to connect. So a lot of pins. You asked if it worked, and it did not. But I worked out why.
Okay.
And then I fixed it. So it was basically the symbol I'd used for the design had the clock, basically a different way of expressing complementary and true clock signals. So on the DRAM chip, it was like _T_C for like true and complementary.
Okay.
And on my own net naming signals, it was like plus and minus. So _P_N. And I connected the N to T and the P to C. So like the clock signal was swapped.
Yeah.
Because it's double data rate, it's looking for a specific sequence, like on a rising edge, on a falling edge. So work that out in a design review. It's kind of tricky because bringing up the board, it's like you don't know, because I've not used this chip before. I don't know if it's the hardware or a configuration I got wrong. Especially because the reference board I had here used DDR3, not LPDDR3. So it's like a different configuration thing. I can't test it on another board either. But yeah, I managed to find the fact that the clock was the wrong way around.
I think I might have seen some photos actually.
Yeah, and then it's like, well, okay, the clock's the wrong way around. These signals go from under a BGA package through a middle layer of a circuit board under another BGA package. It's like, how do I even swap these to try out to see if it works? And on the first board, I ended up just hot air removing the DRAM chip and then kind of cutting out some traces. So basically the traces are dog boned. Dog bone is a type of BGA fan out arrangement. Basically the pad of the BGA has a little trace that goes to a via that kind of sits offset from the BGA layout. So I had this, I had this like little tiny bit of trace that I could cut between the via and the BGA pad. And then, it was a matter of kind of swapping these two signals with some wire. Not really caring that one ends up now a couple of millimeters longer than the other. It's like, well,
okay,
it's better than nothing. Yeah, exactly like that. And so, managed to cut these and put in wires. I think that's a photo I put up on Twitter a while ago as well, because I did this for a couple of boards. I mean, we've got a stack of circuit boards here now that all have this problem. Right. It's like, well, I can order some more boards, but also it's like I've got, I want to make up a couple of prototypes to validate.
Prove it out. Yeah, exactly.
I did this on, I think, five or six boards.
Okay, well done. I know a lot of the issues can come, even if they said, here is a layout, use this, nothing else. A lot of the potential issues could come downstream when the bootloader, the early boot stages, actually set up and configure the RAM interface. And if you're not using their layout, you might suffer from sort of timing issues and things. And if you haven't got access to the registers or whatever else, then their binary can cause pretty significant problems. So I'm glad that wasn't your issue. That could have been very
well, I mean, that's what I thought initially, because kind of trying to think about all the possibilities of what's wrong, and then talk to the via like the sales rep to get to some applications engineers about how can we get this to work. I'm using a chip that's on an Excel table that says that it should be, well, there's a chip on an Excel table that says it's compatible,
right?
But I can't use that because I can't find it in stock anywhere. So I'm using a similar one. But my opinion is, I think most DRAM chips should be interchangeable, especially on something like this where it's not running at crazy fast speeds or anything.
I think that's the whole point of GDAC, isn't it? It's gives you that confidence that it's going to work. But that's anyway.
So but with that, basically I swapped the clock lane, put the chip back on, and it works straight away. So it's like,
well done.
Like after all this fiddling, I probably spent a couple of weeks, poking around at this on the configuration side of things, trying to get it to work and not getting anywhere. And then just the fact that I messed up the layout.
There you go.
But that's where rework skills come in handy, right?
Oh, absolutely. Yeah, that's something that I need to brush up on, fully admit. We've had a question from Victor about, I think that's reduced pin count RAM. Do you know anything about that? Can you give us some insight? I'm not sure if Hyper RAM would count as that.
Yeah, no, I could actually, they're in another room, but I actually have some chips here. So RPC RAM, reduced pin count. It's specifically a type of DDR3 at its core, but it's a different kind of controller interface. So instead of needing a fixed width address bus and a fixed width data bus, clock signal, and then some other extra signals like write strobe and row select, activate, stuff like that. It operates over, I think it's 12 pins. exactly, which is basically like an 8-bit data bus and a clock signal.
Okay.
And and there's like a single pin where you can, instead of the loading addresses in a parallel manner, you can actually serialize your address of like the next instruction and send it through. Or you can send through, like HyperRAM, you basically use the data bus to load in an address.
Mm-hmm.
It's like, oh, I want to read from this bank. So it's kind of more commanded transaction based.
Yeah.
Well, I guess DRAM is transaction based, but it's over a single bus.
Yeah.
Right. Over a single bus.
Nice.
This kind of was designed on like a bit of a limited release, I think maybe about 5 years ago. Like, it's been around for a while, but I think it was only about 2 years ago that E-tron released chips that you could actually buy. You can buy them off DigiKey now.
Okay. I have to admit, I've not heard of reduced pin count RAM at all. So
so
I kind of jumped to HyperRAM possibly.
It's
but
a bit of a chicken and egg problem, because now it's pretty easy to get the chips, but what can you plug them into?
FPGAs clearly.
So I've put some chips onto Orange Crab boards.
Right.
Like, I've got some here, and there's already some code in Litex's Light DRAM package to support the RTX 7 from Xilinx. So that's already there. And I was asking about this like a week or two ago, I think, because every now and again I look over my shelves and it's like, oh, right, I've got this this project I started. Like, I soldered it up on a board and started a project looking into it, but kind of didn't get very far. So I think the A7 support is basically fully complete. And then what's possibly more interesting to me is to get on the ECP5. You need a bit more of a front end. The developer of Litex said that it's probably to get it in, it's probably like a solid couple of weeks from a developer, or some very passionate hobbyist. Probably if I had found the time, would be where I sit.
Yeah, fair enough.
And it's interesting because with 12 pins, the chips are actually available in a wafer level chip scale package.
Right.
So if you look up the marketing for them, it's like about half the board area than the HyperRAM chips currently are, and you get it's all for DDR3. It's always depending on the type of memory accesses you're doing. But you can get faster bandwidth than HyperRAM.
The page I just pulled up just now, it says 256 megabit up to 4.8 gigabits a second, which is quite considerable.
And that would be kind of streaming out from banks, probably in parallel, like separate banks through the chip. I think the market for that, or one market they were pushing for specifically, was like lower cost, high definition TVs or high definition displays, where you want a frame buffer. But you don't want to have to, or you're trying to miniaturize a device with a high def screen. A DDR3 chip is quite a large chip nowadays on a board compared to everything else.
There you go. Fascinating.
Thank
you for the info.
But not made too much progress on the ECP5 front of that. But
no, fair enough.
Hardware in the works for somebody that's got enough time, more than anything, to look at it.
Very good. So I'm not sure if you'd like to talk about some projects. Obviously, you've got your LED D20 that you've probably talked about a lot. And I think you showed that to me just now, saying it's in pieces a bit. Anything in particular new on that project, or is that sort of been completed for a while now, and it is what it is.
Yeah, it was completed for a while, and I had it just on my shelf in pieces.
Okay.
We have
I wasn't sure if the
This
controller came out for good reason, or
yeah, so this is kind of the frame with all the little bits. Some panels are still there. I think, yeah, if you saw this at at the last Chaos Communication Congress, I think before that, so I took it to SuperCon in 2019, and then to CCC. I'd glued in the panels. Well, I'd used some kind of not two-part, like silicon sealant, I guess.
Okay.
It's probably the best way. So it's like a little dab in each corner, and then just kind of stuck the panels down. So they're actually kind of a little bit tricky to remove. To almost douse the whole thing in isopropyl, it kind of dissolves away a little bit. Managed to remove most of them, but I was trying to get to the core, which is this controller board, which I don't think the lighting's going to work here, but it's basically a SAMD 51 and an ICE 40 FPGA on there. And then there's some power supply stuff, and I think there's a 9-axis accelerometer, gyro magnetometer at the top there. I programmed the SAMD 51 in Rust, just because I was interested in how Rust works. And I don't know if that was a mistake, because specifically the SAMD 51 isn't actually very well supported in Rust. Like the crate for it is kind of limited. I had to write my own DMA driver and stuff. It's interesting, but I basically got it to a point where it's just showing kind of interesting static animations. And I think a cool next step would be to, which I've been saying this ever since I built it, but I've not got around to it, would be to add some kind of wireless interface to this, like, Bluetooth or Wi-Fi, probably with an ESP kind of module in there. And you're not being able to get FPGAs for a while, and like the Raspberry Pi Pico has been released since I designed this, and so I'm thinking I could use the Pico to do the low-level display driving, to replace the FPGA that's on here, and that also saves on cost a little bit, but that it doesn't really matter for a prototype. But throw that in, and then I'll maybe like an ESP-S3 or something for the hardware. With some of the other projects I'm on, I'm like, ooh, I could put an embedded Linux computer on here, and that would give me a lot more grunt to do. Like, basically with the IMU, you could do stuff like display like spherical content, like a globe or something, and when you rotate it, the globe is rotating on the displays, in an interesting way. And I just don't think I've got the grunt to do those kind of math operations on the SAMD 51. And then this one, you've got to unplug it and plug in a USB cable to reprogram it and stuff. It would just be nice to get to a point where you could do animations on a computer, or effects on a computer, and have it just running on the D20. And then I've also got the cube that I built as well. That's like a miniature LED cube. I've already got designs I've started to kind of shrink the panels down to be a bit more closer to this size.
Right.
Like handheld, and the cube is quite a bit larger.
Okay.
But Yeah, it's about finding the time.
Oh, of course. Yeah. Very good.
And it kind of feels like I'm just rehashing an old project. It was kind of fun to get it to like push through and get it to this point, and now it's like,
Yep.
well,
I
it'd be cool if it
completely
did
get
these
that.
other things, but
Yeah.
it's like I've kind of already done the main project. So.
It's finished. People have gone, wow, let's find something else fun to do. Is that kind of the mindset you're in?
Yeah, a little bit. But it is, it's like an interesting, like flashy project, whereas a lot of other stuff I do is it just ends up being dev boards or
Yes.
it's purely software only.
Well, speaking of
got
dev
another
boards, you're playing with the butter stick. Yeah, this one. Yeah.
Yeah.
And I saw you mentioned the other day you're looking at getting DVI up and running on the butter stick. That's pretty exciting. Do you want to talk about that a bit?
Yeah, so I've already got already set up. It's basically DVI over a HDMI connector. Is
Yeah.
the simplest way to run HDMI compatible signal from an FPGA.
Yeah.
There's projects available that let you do the full HDMI specification, which basically gives you a couple more encoding options and lets you do an audio stream through the cable as well. But they're a bit more complicated and they take up more resources of the FPGA. So it's easy to stick with just the DVI implementation. I've got that one working on the standard I/O from the butter stick.
Okay.
So all the I/O pins on the ECP5, which is the FPGA on the butter stick, they run up to 400 megahertz, or 800 kind of. If you're using the DDR terminology, 800 mega transfers per second. So kind of you can basically lock data in on the rising and falling edge, even if it's only 400 megahertz to the kind of to that double data rate register at the I/O. And that's enough to get up to like 1080p 30 frames a second, or 720p 60 frames a second, right? They're actually the same bandwidth. To get up to 60, you have to go beyond that rated I/O speed. And it works. You can push the chip to do this, but it's like you're kind of outside of its operating parameters at that point. Right. So I see Conrad
have you done that?
had
does it work out?
Yeah, I've pushed it 1080p 60 before.
Nice.
Timing errors everywhere, but it does work. And like some displays are more fiddly than others. Some start showing a couple of artifacts, and but it locks onto the signal and will show you something.
Interesting. And what's the side effect? Is it sort of considerable extra power usage, or the fact that you're operating up out of its technical range?
I mean, the side effect's just that it might not work, and there's nobody you can blame but yourself.
Of course, but
you're kind of using the chip further, further outside of its operating range. I mean, I guess the main problem would be that the I/O just can't switch down to like a low to high level fast enough. Like the edge rate isn't really fast enough, to make sure that the display is seeing like a consistent high-low signal, right? So I think it's kind of within
boosted voltage 1.2.
Well, on this specific ECP5, it is running at 1.2 because it's the SerDes enabled 5 gigabits per second model, which I believe they just bin them, and then some of them they can run at 1.2 volts anyway. I think it's the same die inside.
Right.
Anyway, the new work is basically to run this signal off the SerDes.
Okay.
So the SerDes is rated up to 5 gigabits per second, like toggling rate at the pin. So if the signal ends up being compatible enough to drive a HDMI display, because it's a little bit of a different signaling mode, it could be interesting to get it running through the SerDes, because it means that you actually are running the chip in a mode that the manufacturer has blessed you to use.
Yep.
And it kind of offloads all of the high-speed serialization. So the SerDes in the ECP5 can do 20 to 1 SerDes ratio, or like 10 to 1 or 8 to 1. It's pretty flexible, but 20 to 1 would let you basically load 2 pixels worth of data on every clock cycle.
Yep.
So it will let you run basically the logic behind generating the screen content at a much lower frequency than the actual pixel clock, which increases your timing headroom and lets you put more logic into that generation kind of block. So I've been trying to make use of this with the open source tools like Trellis, Yosis, NextPNR, which it's all compatible on the, like, it's all documented on this like black box with these inputs. Will get you to a bit stream that then runs, but you don't get the benefit of the Diamond toolchain, which is the Lattice toolchain, which gives you like a GUI that lets you configure the SerDes for specific applications. Like this chip lets you do like SDI or eDisplayPort, SGMII, or what's another one? I think that's pretty much PCI Express is the other headliner. So it's kind of all these kind of fast serial protocols. If you use Diamond, you can just tick a couple of boxes and it generates kind of the boilerplate code for you that then sets the peripheral up.
Yep.
I've had to be going on other people's kind of reverse engineering of what these bits mean, and even that some of the bits, it's like, this is undocumented, but this bit was always one in
seems to
all
work.
the configs I tried. And I think the holdup now is I've managed to get the SerDes running at a clock speed and loading data in at 10 times slower than that clock speed. And I can see all the bits on my scope, but I can't easily ramp up the pixel clock to kind of see at steps that everything's still working. I think I need to jump to the clock speed of DVI, HDMI, and then hook this up to a faster oscilloscope to do any more probing. I think there's some limitations about its own PLL and oscillator that does the divide by 10 or divide by 20 internally. It's not quite as flexible as the other PLLs, and it can't hit kind of every frequency.
Right. Okay.
So yeah, it's been interesting. And I don't know if this board has a date on it. I don't think it does, which is, there, yeah. Yeah, 2021, May 26th.
Okay.
So yeah, it's been about a year, just over a year.
Well, I have to admit that I actually got a butter stick with the intent of looking into a MIPI DSI type debug tool, and I've done absolutely nothing with it yet, which is so frustrating. But you're not alone with the slow progress on projects side of things.
Yeah. Well, I think that's a common plague. You just got to focus on something and then chip away at it over time.
Yeah. But there we go. Are you happy to keep talking for a bit? I think we're a bit over time. But, yeah. Cool. So you mentioned
you can see the window in the background. The sun's coming out here.
Good morning.
It's not miserable anymore.
That's good. Yeah. You mentioned as well you got a wireless soil monitor, which you've been working on, and I think that was a capacitive spike that goes in the soil. Is that right?
Yep. Get the board here.
And this potentially links up with another thing you mentioned, which was your sort of smart home side of things as well. Can you talk about perhaps both of them, or one and then the other?
Yeah. So this is This is based off a design I found on GitHub. There's a couple of them from a couple of years ago. It's basically a capacitive sensor at the top here. So you can kind of see this kind of like probe shape. And when this is basically poked into soil, down to, well, like this line is indicating where the sensor starts, and you kind of push it a little further. And then based on kind of the amount of moisture that's touching the circuit board, that capacitive sensor changes capacitance because it's essentially in a different dielectric depending on the soil. So at the top here, there's a little wireless module that's based on the ChipCon 2630, I want to say, 2530. It's a TI/ChipCon part. It's an 8051 processor with a 2.4 gigahertz RF front end. And specifically, it lets you do stuff like Zigbee, which is what this one's using. So Zigbee is like a low power kind of like sensor battery operated peripheral interface. So this device spends pretty much like 99% of its time sleeping, and then it'll wake up. I think the code I'm running now is every 15 minutes, but the soil doesn't change that often. It could be every hour. It could be every day. I mean, you could stretch it out. It's just when you're developing these things, you don't want to have to wait a day before you see an update on your little graph. So 15 minutes is a good compromise.
Sure.
Basically, it wakes up, runs a PWM signal through a little envelope. I think it's an envelope filter. It's like through a diode and then an RC, or an RC filter, then a diode. And then through the capacitive sensor. It's basically measuring the capacitance, which is a very low capacitance, but measures that based on, sending a pulse width modulation through and then filtering out the pulse width modulation just to get a DC value. It then measures that, calculates. The code is doing something clever, trying to calculate a difference in measurement based on the battery voltage as well. So when the battery voltage goes lower, the readings change. Because you're basically providing a lower stimulus to the sensor, so it's not linear in that regard or something like that. But basically takes this value and ends up with a percentage of like the sensor is dry or the sensor is wet. It's like 0 to 100%, and then that's forwarded through via Zigbee to a Zigbee coordinator that I've got set up on a Raspberry Pi that's running Home Assistant. Which I'd set that up initially to run some. I don't know if you've seen them before. I looked into deeply. All the IKEA smart home devices actually operate over Zigbee.
I didn't know that. That's kind of cool.
So and Zigbee being a open standard, they've done the right thing. I mean, if you're selling a commercial product, I think you basically would have to be complying to the standard. But they're Zigbee branded, and it means that you can make use of pretty much all of the IKEA stuff without needing an IKEA gateway. You can plug it into your own coordinator, your own system. So I've been doing that here. I've used their buttons for a little while. They're so cheap. It's like $10 will get you the. I guess it depends on your definition of cheap, but gets you like the Zigbee button with like 2 buttons on it. You put a coin cell in it and it just kind of works. And so I was using those to turn on some Wi-Fi lights for a while. And then I've kind of one step further, and I bought a bunch of these, which these are from Shelly, but Sonoff makes some as well, which is another popular brand. And it's basically you give it either 12 volts or a mains voltage, and then internally there's an ESP32 that's powered on. It connects to a Wi-Fi hotspot, and then can accept incoming commands to turn on and off a relay that then can turn on and off a mains device. And then you can also feed a switch input into this one. So
like a light switch.
I put these behind a lot of the light switch plates.
Gotcha.
So that the light switch comes in, and then internally it can actually then just switch on the relay. And then you can also send it a command over Wi-Fi to turn off the relay.
Gotcha. Okay.
Or to turn it back on.
Yeah.
In that mode, it means all the switches are in like weird positions, like up or down, which luckily isn't too bad for me. But you can have it in another mode, which lets you always turn on when you like on the downstroke of turning a switch on. But that means that if you come to a room that you turned off via the Wi-Fi command, you want to turn it back on, you've got to like switch twice.
Yep. Yeah.
So I think that's a bit more inconvenient. Alternatively, you can have push buttons as well, but I don't really. I prefer the clickiness of an actual switch.
Okay.
But I put these in just initially to solve a problem I was having with Wi-Fi enabled lights. So I was using some lights from LifeX, which I think is initially an Australian brand, but they've actually kind of gone out of business in the sense that their parent company isn't supporting something correct. I don't know. A lot of these smart home things you want to make sure you're doing your due diligence on.
Yeah.
Specifically, all the stuff I've been trying to do, I don't want any server connected products
that's the thing, isn't it? When that cloud goes away,
if the server went down, I wouldn't be able to turn my lights on. Like I want to always keep my stuff local. That's why I've got the Raspberry Pi with Home Assistant running. And I managed to separate all the smart home devices, make them a little bit dumber by not letting them talk to the internet. But specifically when I was turned off the power to these lights, like when you then turn them back on, they don't connect instantly to the Wi-Fi network. Like it takes a little while to connect, and then sometimes they'll be at a different color, like they won't have saved the color they were on or the brightness setting. So I got these little Shelly relays specifically to basically keep the power to the light turned on and then to intercept the switch signal. So when you turn the light switch, it sends a message to Home Assistant. Home Assistant then sends a message to the light bulb. It's like a very round trip way of turning lights on, but it's all local and it basically happened instantly anyway. So it's all good. I only had one incident where I just turned off the lighting circuit on my switchboard and turned it back on. And then suddenly one of my lights, the relay in the Shelly is turned on to power the light bulb. And when you're switching the light switch, it's sending a message to Home Assistant, which is then trying to send a message back to the light, but it hadn't connected yet.
Right.
So you're basically switching the switch and the light's not doing anything. It can be frustrating, but I kind of know when that happens now and like when and why. So hopefully that won't happen. And I guess worst case, I can put all my lights on a UPS. Something like that.
This is a bit of what's it called, yak shaving kind of thing, where
well, actually, I'm planning to add a home battery actually, which is basically like would end up having the lights on a UPS-like circuit. So then, really, the only failure point would be if like the Wi-Fi network went down, because it's all internal Wi-Fi, doesn't need a internet connection. So I've already proved that if I cut my internet connection, the lights and everything still work. It's
nice.
It is actually working locally. But then that's the next step. I actually did another project where, like the Shelly relays, it's just an ESP32 inside. There's actually a cool project called ESP Home, which is from the developers of from the developers of Home Assistant or aligned with Home Assistant in some way.
Okay.
Basically lets you, without really needing to know C-level programming, lets you program ESP32s with like a configuration script.
Okay.
And you can then, it basically takes care of everything. It sets up like a bit of a descriptor about what the device is based on your config file, and then lets you set up like inputs and outputs or sensors to the ESP32 that then basically just appear in Home Assistant as devices. So I set that up for my fume extractor. I built a little custom ESP32 board that has a relay to basically turn the mains on and off to the fume extractor, and a pulse width modulation signal that runs into kind of this big blower motor that's on the bottom of the extractor that just takes an enable and a PWM signal and modulates the speed, because it's actually a pretty hefty HEPA-based unit. At full bore, it draws about 150 watts. So you can imagine like 150 watt blower fan. It's not exactly the quietest unit in the world. So effective at pulling the dust and filtering it.
I'm sure.
But I don't want to have it on all the time. And the problem was it was all controlled by a potentiometer. Where when you turn it down to 0, you'd hear it click and it would turn off, and you then turn it back up, which meant I had to bend down under my desk and turn this fume extractor up. And you might not get it the right speed, and if you want to change it up, suddenly you're doing a bit more soldering or some work that's going to make some more fumes. If you want to turn it up a bit higher, you've got to bend back under the desk and turn it up. So with this, I've now just got it set up on one of those IKEA buttons. I can basically just push the IKEA button, which is a little wireless button I can put anywhere. It'll turn on, push the other side, it turns off,
Nice.
kind of all works. And all of that project work is actually up on my GitHub.
Oh, cool.
I mean, it was a pretty basic project to do.
It's one of those usability type things, isn't it? Improves your life and makes things better, in inverted commas.
Yeah, and it's actually an interesting one because I managed to finish the project within a week.
Hey.
Well, I was calling it a weekend project, but because it had a custom circuit board, it's actually kind of spread over 2 or 3 weeks. But basically from design, I spent a couple of hours on the design and then a couple of hours building and programming it. That did fit over 2 weekends. And
very good.
An interesting feeling actually finishing a project instead of just starting another one.
No comment. Great. Okay. Well, I think we're probably time to wrap up now, if you're happy with that.
Yeah, okay.
Yeah, thanks very much.
Yeah, no, it's been great chatting with you this morning, this evening.
This evening for me, it's
time
pitch black outside, but
yeah,
it's all good. Yeah, thank you very much. It's been great to have you on. Next week, we're going to be talking with Guy DuPont. And aside from that, goodbye from us.
Bye.